So I'm going to switch over to software here. I'm going to briefly introduce the software I'm going to be using. I'm going to be measuring. I've got a nice little strain gauge bar here that I have plugged into my SCADAS RS data acquisition system. For those who are unfamiliar with the SCADAS RS, it is a modular, rugged data acquisition system. You can see I've got these different modules here connected with daisy chain cables. And one of the really nice things about this data acquisition system is it has software running directly on the hardware. So I'm going to be using something we call the SCADAS RS Recorder app. This is a web app that's, again, running directly on this hardware, so I don't need to install any software on my PC. I just need to connect up to the hardware and type in an IP address, and I've directly accessed the software. And so let me hop over here. You can see I'm just in a web browser. I typed in an IP address for this web browser, and now I'm in this software that we call the SCADAS RS Recorder app.
I don't quite get what you mean by a web app. You mean you're using an internet browser from your PC. You went over to the RS through this IP address through the web browser. So this software is running where?
This software is running directly on the hardware. So the way I like to think of it is my PC is almost acting just like a monitor or a display.
Like a dummy terminal or something.
Sure.
And if I could go to this IP address through my phone's web browser, I'd see the same thing.
Yep, your phone could act like that display, or a tablet could act like that display. This software that I'm viewing here is not actually being run on my PC. I have no installation, I have no license or anything like that. So I've got a couple of different tasks here. I've got this instrumentation task that I can use to set up my channels. I've got this calibration task that I can use to calibrate any sensors that I'm using. And then I can actually kind of set up how I want to take the recording and view the data. I think a logical place to start off here would probably be this channels location, and we'll set up a couple of strain gauges. So I've got a quarter bridge strain gauge on channel 1, and I've got a full bridge strain gauge on channel 2. So I'll go ahead and I'll just start setting these up. It's a quarter bridge. Change my conditioning method to quarter bridge. And then I've got my strain gauge factor. I've got my bridge factor, or this is also the number of active gauges in my Wheatstone bridge. I've got a supply voltage and so on. So I'm going to give this 10 volts. And then let me maybe turn this on, and I'm going to go to this little single channel page here. And just to make sure that I'm actually reading something on my strain gauge, I can flex my little strain gauge bar. I'll kind of do a little sine wave here. And it looks like we're reading some output from the strain gauge. So that's good. And so yeah, so I maybe should have explained, I'm on just a single channel view for this one quarter bridge strain gauge. So I have kind of a live readout here on the left, a time history in the top right, a wiring diagram in the bottom left, and then a frequency diagram in the bottom right. And I can make changes to some of these parameters, and I can, just for example, make sure that this strain gauge is still functioning correctly.
You can make live changes and see how it affects the signal, huh?
Exactly. Let's say, for example, I want to bump up this sample rate. I should see a lot more data coming in here on my scope view. Now it's pretty fast. So we'll lower that back down. But I could even, change my supply value. And that might be nice. It might tell me whether or not I get enough excitation at a lower supply which could be helpful if I'm testing on a plastic part, for example, or using a pretty small strain gauge. I might want to be able to use a lower supply value to avoid self-heating issues on that gauge. One thing I'll point out here too is I can see the actual output in millivolts per volt from my gauge. So, one thing that I think is pretty interesting about strain gauges is the output is very, very, very low, even at very high strain gauges. So I'm only getting 0.57 millivolts per volt of excitation, which is, I'd say, probably quite different from a lot of the typical sensors that you might use, like a pressure sensor or an accelerometer, that are usually a 0 to 5 volt output. But basically, depending on, if we were just to specify the sensitivity in millivolts per microstrain, for example, let's say we didn't do this millivolts per volt, that value, that sensitivity value, would vary based on the excitation voltage that we supplied to the gauge. So depending on whether that was 10 volts or 3 volts or 1 volt, and that just invites a lot of opportunity for there to be some user error when you're setting up this gauge. So by using millivolts per volt, we're kind of normalizing the output based on our supply voltage. Okay, I'm going to take a quick step back here. Let me set up my full bridge strain gauge as well. Set this to full bridge. And then I just wanted to make a brief comment on a couple of important parameters that influence the sensitivity value of this strain gauge. So I've got this gauge factor here. This is typically a value given by the manufacturer of the strain gauges, and I can see if I modify this gauge factor, so I'll call it 2.15, for example, I see a small change in the sensitivity of this strain gauge. So the gauge factor affects my sensitivity. And then we briefly talked about the number of active gauges in my Wheatstone bridge circuit. So that's this bridge factor parameter. And do you see how from my quarter bridge to my full bridge, the bridge factor of my quarter bridge is 1. I only have 1 active strain gauge, and my quarter bridge and my full bridge is 4. I have 4 active strain gauges. So my sensitivity, or the kind of output from my quarter bridge strain gauge, is 4 times larger than that of my quarter bridge.
So one reason we'd want to use a full bridge over a quarter bridge is for the same amount of strain, we get a stronger signal.
Exactly. If you're measuring really low values of strain, we might need more output to digitize that signal correctly. Okay. We'll talk about this a little more in software here, but I'm also going to scroll down here and show you that I've got this shunt branch, shunt reference, and lead wire resistance columns. And so I can actually see when I apply my shunt, I can choose which branch of my strain gauge I want to apply this over, R1 and R2. For a full bridge, I have more options here. And I can see the value when I apply that shunt resistor, what my strain gauge should read. So based on a 100 kilo ohm shunt, if I apply that to my quarter bridge, I should get roughly minus 1,635.2 microstrain. I do have some options to change that in my software. So on the SCADAS RS, we have internally a 50 kilo ohm and a 100 kilo ohm shunt resistor. And so instead of a 100 kilo ohm shunt resistor, apply a 50 kilo ohm shunt resistor. My shunt reference value is now double what it was previously. So a higher simulated strain with a lower shunt resistance. I can also, if I change this shunt branch, see that I go from a simulated compressive strain to a positive compressive strain. Okay, so let me go back to my single channel page here, and there's maybe two more things that I'd like to discuss. So one of these is I have a pretty large strain offset here on this strain gauge bar. So what I can do in the software is I can zero this channel. I'm going to go ahead and do that now. And after I perform that zeroing, my bar now reads roughly 0 strain, and I store that measured strain value in this field in the software called offset EU. So if I wanted to add this back to my strain gauge signal later to, let's say, account for the preload, either the negative or positive mean stress, I could certainly do that. But now I've just got a strain gauge value that reads 0, which makes me happier when I'm performing a test. I kind of want to see what the strain value is. The other thing I'd like to talk about is the effect of lead wires. So in our software, we have a location where, if desired, you could input the lead wire resistance of the lead wires going to your strain gauge. And this is because the longer the lead wires to the strain gauge, the greater the voltage drop between the DAC and the strain gauge, and that could cause some percent error in the actual measured strain signal because we're not seeing the full excitation voltage at the gauge directly. And so, Pete, you could, when you're performing your test, take out a little voltmeter and actually perform this resistance measurement and then stick that directly in here. And you could do that for all 100 of your strain gauges. Does that sound like fun to you?
That does sound like fun.
A nice afternoon in the office. Instead of doing that, we can do the lead wire correction directly in the software. So I'm going to go to this little lead wire calibration task here. I can see my quarter bridge strain gauge. I can see some parameters for that strain gauge. I'll go ahead and select start the calibration measurement here. And it essentially performs a shunt calibration, so a measurement without and with the shunts applied. And based on those two measurements, I'm able to calculate a new lead wire resistance, and the sensitivity of my strain gauge is updated accordingly. So you can see I went from a lead wire resistance of 0.7 ohms to 1.07 ohms. I can go ahead and apply that, and now I'm happy. I've essentially lead wire calibrated this particular strain gauge. Okay.
And then you might even be able to zero after that, huh?
Yep.
Looks
yep.
like.
I certainly could. And depending on how you're performing your measurements, it might even be desirable if I go to this measure tab. I'll go to recording setup. I might want to zero all my strain gauges before every measurement. You know, maybe there's some strain drift due to the heating of the gauge based on your excitation voltage, or some sort of drift due to other reasons. If you'd like, you can automatically zero that out, so you're starting at 0 strain at the beginning of every measurement. Okay, I think that was all I wanted to cover in this webinar.